Okay, I think I think we can start. There are still some noises outside, but I will take a part of my time. So it's 2 minutes. I will take part of my time to introduce the session, not only my talk. So my talk will be the first of the session, and then there will be other 4 talks after me. So this session that I organized is basically the main idea was to put together people that are working in a project, international project, France-Taiwan, that is related to distant geometry in the context of structural biology. And but if you see the program now, this is just a few pages concerning our session. We changed the name because for organizational reasons we have also talks that are not related to structural biology. So the new title of the session is distant geometry, graph embeddings and applications, more general, not only biology, because there will be my presentation. It was not supposed to be in this session at the beginning. Then, because of the methodology, the distant geometry is the same as the other presentations, we decided to include it here. And we have also another, let's say, guest talk from somebody out of our team, this project team, that is going to be on even another application where there are some dynamical aspects of geometry. Okay, so. This is what I wanted to say at the very beginning. Now I can start with my own presentation. This work started. Let's say the idea behind this work started exactly 2 years ago, when myself and another colleague from University of Waterloo in Canada. We organized a mini symposium on central network localization and dynamical distant geometry. And unfortunately, at that time, we were not in Toronto. We were online. Everybody was home because it was exactly 2 years ago, as I mentioned. And so you can see the presentations looked like this. So you have the slides and the guy in the little corner. And this guy, David Pelta. After his talk, he had an open question, an open problem. He proposed us a particular kind of problem related to the application in adaptive maps. So what is an adaptive map? I didn't say yet. I will come to this point in a second. And in the audience, and there was also my PhD student that is here, Simon Engeveld, and he was talking about other stuff. But it's a little related to the talk that we'll have, the third talk about animations and dynamical geometry. And so together with Frank Plastria, that was in the audience, he didn't give a talk, but he was in the audience. We started to work on this, on what was going to be finally the paper that we presented in this conference. So now, what is adaptive maps? Here you can see the map of Rennes. Rennes is the capital of Brittany. It's probably, okay, you are from around here, maybe, or if you are not from around here, maybe you had to travel to Rennes before coming here. And this is the geographical map that the Google Map proposes, where the Euclidean distance is predominant. So if I want to go from a point of interest to another, basically the distance between these points of interest is evaluated through the classic Euclidean geometry. Now this is mostly flat. It's not really flat, but like we can suppose it's flat. So if I want to go, for example, from this point, this is the train station, to this point is a quite famous park in the city, in the middle of the historical center. Then the distance that you have to travel is more or less the distance that you see here. Now, in other situations, instead, we would like to adapt the map by taking into consideration the mobility capabilities of the user, or the map user. So now I make an extreme example. I'm in wheelchair. I would like to go from the train station to the park. Now, the Euclidean distance is exactly the same that I need to to cover, but if the train station looks like this, you know, it's quite modern, was finished quite recently. If I'm in wheelchair over there, I can go in every corner because it's a modern construction. The Parc du Tabor, the entrance, looks like this. So this is an old postal card, but didn't change. The steps are still there. So I'm in wheelchair. For sure, I don't have wings that will allow me to fly over these stairs. And so the distance for me, for this person in wheelchair, between the train station and this particular entrance of the Parc du Tabor, it's not the same as the one for somebody in normal mobility conditions. And so this is the basic idea behind the adaptive maps. We want to deform, we want to distort this map in such a way to take into consideration this kind of limitations. Of course, here I'm considering, as I mentioned, this is an extreme case. I should put a hole in the map because somebody in wheelchair will never be able to do this. We can consider different situations. For example, I was mentioning Rennes is mainly flat, but there are other cities that are not flat. And if I can walk, but I have some problems, let's say I'm a woman and I'm pregnant, I don't want to climb something very steep, or I'm carrying something, I don't want to carry something on something very steep, then my distance between the 2 points of interest may be larger. Or other cases can be simpler. I can have some something that makes my trip easier, and so the distance can be shorter in this case. Okay, so this was to introduce the main ideas. Now let's make some simplifications, because I will not be able to solve right now the entire problem until the end. I will not show any deformed maps by using this kind of approach. I will rather make the first simplification where the details of the map are, as you can see, are erased. So if I want to go from the Gare to the Parc du Tabor, I know that I have to take some small streets. I'm not a bird. I don't go from this point to the other. I connect them with one line. I need to take small streets, but these details are not in the models at this moment. So they will be added later. And I also consider that my graph may be, so I can connect the different points of interest with an arrow in the graph. And I may have the situation where the graph is full, it's a complete graph, or some situations more like in this case, where the graph is not complete, so some information may be missing. So consider now that even though this graph is embedded in 2D in the original map, the distances that will be associated to these arrows, to the edges of this graph, are not Euclidean, are not supposed to be Euclidean. Otherwise, we come back to a classical distance geometry problem. Instead, in our case, we suppose that the distance information is not Euclidean. At the very end, I will show for this example, a solution that we found. And for that solution, we were considering walking distances. So the distance is the time. In practice, the distance is given by the time that a normal walker takes to walk from one point of interest to another. Since the Rennes is basically flat, this corresponds more or less with Euclidean distance. So that's why it's an easy example that I'm going to show at the very end. Okay, so the paper that is in the proceedings looks like this. I put the nice picture of the conference aside, and I'm recalling the paper because here, this is something new that we are I've been working on distance geometry since a while, but this, as I mentioned, this project started very recently, about 2 years ago. And so in our paper, so when it was maybe like 6 months ago, we brought this paragraph. We say that there was a first reference. That was David that was working already on this problem that gave us this seminal paper reference. Then there was some citations about conception metro maps. And then more recently, this is the part of David's work. So there was not so much stuff in the literature, apparently, but then I remembered that I had read the paper already, that where the problem that we are trying to solve was already considered, but not exactly the same. But it's good to give to recall this. So in this paper that is about Euclidean distance geometry, basically by using a matrix representation of the problem, there was an example at the very beginning of the introduction where they talk about Swiss trains, and now the example in the second page, I simply put it here now. And in this example, they reconstruct in a very simple way I mean, not very detailed, but they reconstruct the map on Switzerland by using the timetables of the trains connecting the cities. It's more or less what we are trying to do. Instead of using the Euclidean distance, we use an alternative distance metric, which is not Euclidean. In this case, the train timetables. But okay, so it looks like somebody did already, but no, actually in the proposition of David at the conference in the Fields Institute, there was also an additional constraint. This additional constraint comes from the fact in practice, the main idea is that main users of these possible adaptive maps will know, most of them know already the original map. So if I was in rain already, I know where the different things are located. Now, I may be in the need of using a map that is adapted to my mobility conditions, but I don't want to have things, points of interest, like this Parc du Tabor, that I know it's located more or less in the center of the map. I don't want it to be located now in the north or in the south, in some corners of the map. And in most of it, I don't want that the points of interest are scrambled around in the map, because I will not understand anything anymore. So for this reason, we add in our model the constraints that you can see in the slide. And these constraints basically allow me to ensure that if one point of interest is in the northwest part in comparison to another point of interest, then in our solution this condition is satisfied. So all the local orientations are preserved, needs to be preserved in our solutions. Then in the upper part, maybe I didn't insist so much on this part because I tried to skip things because I already have only 7 minutes left. But let's say very quickly, in the distance geometry, the traditional formulation, you may have Euclidean distances. So and if you know that these distances are given in rather precise, with a good precision, and you know that the solution exists, the problem is basically a decision problem. So I mean, the problem asks whether an embedding of the graph exists such that the distances that you have are satisfied. In this case, we cannot have this formulation, because we know that the distances are not even Euclidean, and then they can even carry some errors, experimental errors, and measuring errors. And so what we try to do is to minimize a penalty function where, in practice, on this side, this term corresponds to the measured distance in the map. So I brought in 2D because we adaptive maps mostly we are in 2D, and this is the distance that I know, but this is not Euclidean distance, as I said. In my example later, this will be a walking distance, so it will represent time in seconds to connect two points of interest. And so now, in general, another thing that I didn't mention for lack of time is that this distance geometry problem is NP-hard in general. In dimension 1 even it's NP complete, and now we are adding constraints to this particular formulation of distance geometry, and normally we should get something more complex, but actually in our case it will be of help, as I will try to show you now. So just to recap, I have the original map. I cut away all the details of the small streets here, so I construct a graph where the connections represent the distance information, which is not Euclidean. And now I'm adding also some quadrants. So for example, here, this is my Parc du Tabor that is in the middle of the map. If this is another park which is close to university, which is here. So for both cases, the university and the second park need to be in the northeast quadrant of the Cartesian system that is defined by the Parc du Tabor, having a center, the Parc du Tabor. Of course, these two lines, the axis, x and y axis, are fixed for all the Cartesian systems that you can define the different points of interest. Okay, now, so I was mentioning we have this nice penalty function to minimize. One of the tricks to solve this problem, distance geometry in general, is to change distance metric and try to use alternative distance matrices like the L1 or the L infinity norm. These attempts have already been done in the literature. You have some short citations in the slide. And this paper was one of the contributions in the GSI 2017 in Paris. And so in both cases here, we replace, okay, we don't like Euclidean norm because we have this square root, we have the squares here, and so we prefer this one because we have absolute values. It's much easier to deal with, but it's not linear yet. Here you can see you have two absolute values. So the first one, you can add as you know, you can, as many of you may know already, you add the variable here that represents all this, then you replace this thing. Okay, I say this fast, otherwise I would never be on time. You can replace, then you can constrain this variable with two inequalities that then you get optimality, you get the satisfaction of the constraint at optimality. But this you can do this trick only for one of the two absolute values. You cannot do for both. So this thing still requires the addition, the inclusion in the model of binary variables, which also we don't like because the number of binary variables depends on the distances. If my graph is full, then it depends. It goes quadratically with the number of elements in the graph, or vertices in the graph. In this case, I have similar situation. I need to introduce binary variables to linearize, to get rid of all terms that are not linear. But in our case, as I mentioned, we have these nice constraints that were added for preserving the orientations. So in our case, if I can, in practice, I can partition the age set in 4 parts depending on the orientations of V, of the point of interest V, with respect to the point of interest U. And so if I'm here northwest, I know that this constraint needs to be satisfied. This is okay, I hope I didn't make a mistake in the slide, but okay, consider that finally I get these equations. And now I can reinterpret my slide. So this equation is true for northwest and northeast. So because it concerns only the north. So in case it concerns only the north, I know that xu minus xv minus xu is smaller or equal to of 0. And so in practice, when I go here, I know the sign, and so I can get rid of the absolute value. And the second absolute value, the one that is outside, the absolute value that is outside is dealt with the trick that I was trying to explain to you very quickly some seconds ago. And so we have this example now. With this example, Simon wrote a model, I think it's C++, then he calls Cplex for the solution of the linear program. And here we have a solution where as I mentioned, the solution doesn't look so different because walking distances are quite compatible with Euclidean distances in this case because the city is flat. And I pointed out with these red big points the points of interest that moved more in the solution. Also, the others moved, but just a little bit. The position are most overlaps with the original. And the objective, it's written down, is 15. We don't go to 0. It's unlikely that we can go so down. Okay, to end, I spoke exactly 20 minutes now, so I'm a little late, but just to give some directions for the future works. As I mentioned, the axis of the Euclidean spaces, or the Cartesian spaces that we use to define the orientations, right now these are fixed, arbitrarily fixed. Can take the ones of the original map, north and south and west and east. But we found out that there can be some situations where our quadrants degenerate or they become too small. And in this case, our model, the linear program is not. It's too constrained. So some of the points of interest are not enough free to move. And this can limit the optimization of the objective function. And by rotating this axis, we realize that we can get better solutions. Of course, making an exhaustive search on all possible rotations, global rotations now of the map, may be too expensive. So we may lose all the advantages that we were able to get by introducing the orientations. But it's a work in progress now. We are trying to see if we can predict in advance the best global orientation in order to get the best solution for the linear program. And then there are some additional things. Finally, one day, maybe if in 2 years we are back and we talk about this again, maybe in 2 years we will have a distorted map that represents our solutions. And in particular for situations where the constraints are hard, like wheelchair, I have stairs in front of me, I cannot climb them. In this case, how to distort the map to visualize this. This is one of the challenges that we have. And this is the end of my talk. Thank you very much. Don't hesitate if you have questions.